Just give me a second.
Thank you for the introduction. I'm going to pick up where Antonia left off and maybe go in similar and related directions, but with some of the same kinds of questions at heart as Antonia has talked about. So again, most of you are very familiar with the uterine pressure and FHR signals that CTG is based on. And of course, there's been a lot of motivation to do better analysis, interpretation of the signal, considering the high degree of false positives, unnecessary C-sections, which are costly for mothers and babies. Just as a cautionary tale, I came across this paper recently, and it would seem that our work is finished because the sensitivity was really good and the specificity was really good as well. This was using a convolutional network to detect hypoxia. And they used a well-known database that many of you have been involved with. When I run into these numbers in my own work, I have a moment of elation, and that followed by some healthy skepticism. So I would put it out to my colleagues here working in this area to look at this paper and see if you can at least it's out there right now, and it's maybe a service to the community to be sure that we understand where these numbers came from and maybe how they fit into the big picture. We're working with a Gates-funded project on a large database, 15 hospitals from Northern California. The idea is that we'd like to apply all the methods that we have at our disposal, from statistical to deep learning to traditional clinical information. I mean, we have the CTG signals, and we have all the clinical data surrounding them, the pelvic exams, for example, the dilation progression is perhaps a very interesting way to assess the progression of labor. This is a big project, and we're very excited about it. Out of that 250,000, of course, not all have gases, as Antonia alluded to, but the fact that a baby doesn't have gases is often correlated to that baby being a normal. So one of the big challenges, of course, is that in developing these kinds of classifiers of hypoxia and fetal distress, the state of the baby is not a static thing at all. It's progressing. So having a good indicator of the baby's state early in labor is very difficult. We can give a ground truth label at birth, but before birth, it's a big research area, I would say, to give reasonable estimated targets for the baby based on a reasonable trajectory to birth. And I think unsupervised and semi-supervised methods that are being developed very quickly these days can help us a lot. I'm going to talk a little bit about, I mean, like Antonio said, I go from the extreme end of the spectrum where you just apply the raw data to CNN and long short-term memory kind of network in a deep learning context, to statistical indices that we have a sense might get to something interesting in a way that's understandable, and perhaps it will give us clues about how to do it as well, or perhaps better, with deep learning approaches. So one of these approaches that I'm looking at is a continuation of an interest that I've had in the coupling of the fetus with the mother. I mean, one of the advantages of CTG and transabdominal fetal ECG is that it's non-invasive. But also, we do have the advantage of having a non-invasive way of estimating how the fetus is reacting to the mother, and especially the insult of contractions. How does that impact on the baby, and can that be informative if we model it well? So transfer entropy is a continuation of mutual information, which many of you would be familiar with. It's based on entropy concepts from physics. If we can reduce the amount of uncertainty by observing an input, reduce the amount of uncertainty at the output by looking at the input, how can that help us understand what's going on? Because a reduction in uncertainty in layman's terms is equivalent to information. And of course, information is the name of the game in this field that we're looking at, when we have these CTG signals that are full of data, but not so full of information. Mutual information is symmetrical, so that if I want to know how much, for example, the maternal uterine pressure and the fetal heart rate are interacting, it's the same mathematics in the inverse direction. So that's what transfer entropy is based on, except that transfer entropy is directional. And in this case, we are most interested, I believe, in the effect of the mother on the baby. So what variables from the mother can impact on the fetus? And of course, looking at uterine pressure and FHR, fetal heart rate first. I'm not giving you all the mathematics to make this talk a little bit quicker, but many of you know that these are based on estimates of probability densities, and how that is done is important, actually, to get a rough idea of a probability density. We often use a histogram, and that's the first step to do it. But there are better techniques now that are more robust and less susceptible to the noisy conditions of many biomedical signals, and certainly to CTG. This is the basis of a paper that is currently under review. I used a toolkit from the University of Göttingen called the Information Dynamics Toolkit to help estimate the transfer entropy. Basically, transfer entropy is looking for how much of past history of the input, the uterine pressure, affects the current value of the FHR now. And if you think of late decelerations as being informative about fetal state, if I translate that to this context, earlier correlations between the uterine pressure and the fetal heart rate could be indications of longer response times and maybe more fetal compromise in the central nervous system of the babies, trying to respond to the impacts of the mother. So for this smaller study, I used an equal number of normal and acidotic babies, but also it had some HIE babies, 42 out of and 250 from the other set. These had 3 hours of recording, and they were normal babies clinically otherwise. Some pre-processing to remove the baseline effectively, because I'm interested in the oscillation parts of the signal as a first step. I looked at 20-minute segments of the signal. This is the uterine pressure, fetal heart rate. These are intermediary signals that are the local transfer entropy, and then there's a global entropy with a lag. The lag time is very close to 0. I look for negative lags because sometimes the uterine pressure mechanical delays can impact on the actual phase differences between the uterine pressure and the FHR. So basically, the story of this slide is that the normal baby had very little delay between the uterine pressure and fetal and FHR. But for an HIE baby, the delay was close to 35 seconds with a UP and FHR as shown here. Now, if we look at the mutual information first, over time, the red is the HIE babies, the very sick babies, and the blue is the metabolic acidotic babies, and the black are the normal babies. So low mutual information for normal babies, progressing to more and more coupling from normal to more severely compromised. So this is the last 3 hours of delivery, and the asterisks show where there's a statistically significant difference between the normal and the HIE babies in red, or the blue for the acidotic babies. So there was a lot more difference with the and earlier difference for the HIE babies. There seems to be some gradation in the mutual information values for acidotic babies, but it's not quite at the same statistical level as the HIE babies. And then interestingly, this is the actual delay. The delay was significant in the last, say, 80 minutes of delivery. So that's just using mutual information and usually using good estimates of the mutual information, not standard binning or histogram, but Kraskov is a nearest neighbor approach that gives very robust estimates. On the transfer entropy side, the surprising and interesting thing about this is, while the mutual information was increasing with pathology, the transfer entropy was decreasing. So if we go back to the definition or the motivation for transfer entropy, what information does the past of the input, X in our case, uterine pressure, provide about the future of Y, in our case, the fetal heart rate, that Y in itself did not provide? In a sense, once you've removed the autoregressive part of the fetal heart rate, that's predicting FHR very well. But what is it in the uterine pressure that's really coupling with the fetal heart rate. And so that was what was really interesting, that the coupling measured by transfer entropy was looking at that coupling in a different way than standard mutual information. A further step that I'm in the process of looking at is instead of just looking at uterine pressure and FHR coupling, looking at the coupling of maternal heart rate and FHR in addition to the UP FHR coupling. So we have two signals from the mother. How does that impact on the baby? And there are the toolkit that I'm using is actually multivariate, so it can handle any number of couplings that you can imagine, and any combination of those couplings from what you consider source and or the stimulus and what you consider the response. So I'm looking in the future to improve the robustness of this index, because noise has an impact, of course. And this step of the research was to really look at that index as for statistical significance, and then to look at it in terms of discrimination. And for that, I'll of course use all the information that I have, either explicitly as baseline and heart rate variability, or implicitly through deep learning methods that can get the same thing and perhaps do it in a more complete way. Because every filtering decision that you make has some consequences. Detrending, for example, getting rid of that sky high baseline so that you can look at the small little oscillations of X cells and D cells, that can remove some of your longer term trends, longer term D cells, for example, which you can be very informative. So again, what I'm following up on Antonia's point, I think the combination of all of our more classical methods with deep learning methods or other machine learning methods that are coming out like in a torrential form these days is really important if we want to come close to the 99% sensitivity and specificity that would be very helpful for babies. So thank you so much.
Very much for your presentation. We have time. We have for a larger discussion now, and we have a lot of questions.
Thank you. Very quick one. Going back to the Gates-funded study, that's very impressive. Has that completed? It's news to me, so I would like to know more about it. If you can share with us. Thank you.
So what's interesting is that we have kind of a heterogeneous source of data. So one of the problems that I've found, and not in this domain, but in other biomedical signals, you can collect under the protocols of one hospital and find that those do not generalize to another hospital. So having a large set of not just cases, but institutions, I think is really important to this study. At the University of California, San Francisco, we have a pediatric neurologist, so she looks at MRI work all the time, so looking at when was the HIE, for example, kind of a chronic condition, and when was it acute? Because clearly, if it's chronic, there's not much that we can do in terms of decision making to change the outcome. But more importantly, technically, it would seem that it would be important to partition that data out and look at it in a different way. Not to exclude it, because it's clearly informative, but it's a different kind of data than a baby that has degenerated close to labor. Yes. The clinical settings that we're targeting, one of the Gates conditions is that this has global impact. So we are going to throw everything that we can at our model for high income countries, and then kind of peel off those ideal conditions in terms of what information is available in a lower tech and more restricted clinical setting.
Okay, thank you. So,
Was that?
My question is, you talked about interactions with other things. Was that by external thermometer, or was that with pressure?
Well, both. And one of the important...
A whole bunch of patients, but community patients out in Northern California aren't
Well, I can't give you the exact number, but I think the problem is even more complicated. So the sensor can change during monitoring. So knowing what the sensor was, whether it was a tachycardia, a tachometer, or an internal, is important for the modeling and for making it useful clinically, because knowing which one is used in real time will be important.
comment that has to do with, you said that one of the variables you're looking at is internal modeling. And in the course of the several cycles, there can be a very little change. But you may get significant changes in blood pressure. And what's going to do that? Beautiful sample usually is most likely to be fusion pressures. You're looking at the relationship with mother and fetus, because if blood pressure is too low, you don't get the fusion which will displace pressures. The spiral arterial is too low. That's the reason for the delay. You see changes in the other parameters. You don't see that with other mothers.
Yes, and probably maternal heart rate and uterine pressure are quite correlated. So maybe something like blood pressure could add a more independent information than those two alone. So that would be a good thing, especially since blood pressure should be readily available. Maybe not continuously, I'm not sure, but sporadically, yeah.
If I'm not mistaken, there was some change in entropy toward the end of the 3 hour.
Yes.
The entropy is likely to change, not only depending upon whether the mother is pushing or not, which is what I suspect you were showing, but it will also change depending upon whether the mother has epidural anesthesia, and it will also change whether the mother is on her side or her back. The cardiovascular dynamics are quite different in those positions, and the relationship to contractions is also different depending upon the position of the mother. And I suspect you could clean up, improve some of your...
Yeah, that would be good to try to control for those
some
things.
of these.
See
They clearly change heart rate pattern of the mother depending upon whether your position is lateral, whether she has epidural or not.
Mm-hmm.
Okay, I'm sorry. Have you looked at Taken's theorem, and have you worked with it? And if yes, how does it relate to directed entropy? Taken's theorem was
I've come across it. I haven't used it.
in 1981, and now it's used in dynamic systems and in coupled dynamics with coupled states, and the language that he used is very similar to the ones used in Taken's theorem.
I see. In terms of the
terms of reading the,
what was not
reading the getting information from one random variable to another, from the history of one to predict the future of the other, and vice versa.
right.
In fact, it is used for discovering causality. What causes what?
That would be something I'd be interested to
Yeah.
maybe there's some connections there that are useful. You know.
Right.
Hi, Philip. Enjoyed your talk, as always. I think for me the key slide was the slide where you show HIE instances and instances with low pH and the controls. And what I would love to learn is the cases with HIE. Do you have information there on how many of those actually had low pH? Because I think this is one of the key things that we need to start taking into account, that most instances with a brain injury actually don't have acidemia, and this will be an important point to distinguish with approaches like yours.
Okay. Yeah. Thank you.
Okay, we have time for another question. Yes.
So you use transfer entropy as well as the mutual information, and it seems like the autoregressive portion is removed with the transfer entropy. I was wondering, wouldn't the mutual information measure give you improved sensitivity and specificity that way, because you're not removing information such as the autoregressive portion?
Well, I think it's looking at it in a different way. Not to say I'm not interested in useful information. Perhaps mutual information and transfer entropy could be both used. But the fact that it kind of isolates the coupling in a different way than strict mutual information does was the interesting finding there.
Yeah, it's a different perspective, if you will, but to kind of, like I said, it isolates that component.
Mm-hmm.
All right. Good talk.
Yes.
One more question.
Yes. Okay. One last question.
Yes.
We have worked with cross entropy. I don't know if it's the same as transfer entropy. As far as I understood, we have
But
got
there's a myriad of entropy
Yes, okay,
measures. Yes.
It's a kind of tool to analyze mutual interactions.
Mm-hmm.
We have got similar results in exploratory studies. But you use cross entropy. I'm not a mathematician, so I was curious if transfer and cross. Okay, there is a myriad of probably measures I'm looking at. Really. Okay, so thank you very much. It was very, very nice.